So we're going to differentiate between mass and weight. Mass is a measure of the actual amount of matter, so they're like the number of moles really of an object, and mass is measured in kilograms. A mass does not change no matter where you go in the universe. However, there's something called weight that is highly dependent on the mass of the object, but it's also exceptionally dependent on the mass of the planet or any universal body, a star, a meteorite, whatever, that the object is close to. Why? Because if we think about it, F is equal to G m1 m2 over r squared. So weight is a force, and the mass of the first object counts, and the mass of, let's say, a planet or a asteroid or a meteorite or a star or something has got a lot to do with what the weight is going to be. But remember what weight is. Weight is mass times gravitational acceleration. So it's going to depend on the gravitational acceleration of that particular planet. We'll get to that in a bit more detail in a second. Weight is defined as the gravitational force that the Earth exerts on any object on or near its surface. And so it is a downward force. Weight is a force, and we can call it the force due to gravity. Weight is a force that is measured in newtons, and weight is mass times gravitational acceleration, and we've been doing this since grade 9, so it's not very difficult. The Earth exerts a constant force of attraction on all objects on the surface of the Earth. That is the gravitational field strength. So all around the Earth is an area of space in which the Earth is able to exert a force on a body, on various bodies. This gravitational field strength causes all objects to accelerate uniformly towards the Earth, 9,8 meters per second squared. Obviously, when I'm a little bit further from the Earth, I'll have a slightly lower acceleration, and if I'm closer to the Earth, I'll have a slightly greater. But it really is very slight until you are well away from the Earth, so we're going to go with a nice average of 9,8 meters per second squared. This is gravitational acceleration, and we've used it already in equations of motion and stuff like that. Here is a video just showing the fact that all objects in the universe are attracted to the Earth with exactly the same force, and regardless of their mass.
Galileo had a big idea. His idea was that all objects fall to Earth at the same speed, regardless of their mass. This experiment shows that Galileo was right. As you can see, the feather falls slower than the coin does. This is because the feather and the coin are falling through air, and air is made up of stuff. And this stuff pushes up on the feather and the coin. This is what we call air resistance. Now, air resistance has two factors. One, the mass of the object, and two, the surface area of the object. So our feather is very light. It has a small mass, but a very large surface area. So that means it falls slower due to air resistance than the coin does.
So this is just a vacuum taking out all the air from that particular tube.
So now we've removed all the air from the tube, and we've eliminated the air resistance. Now our coin and our feather will fall at the same speed. Galileo was right.
So, if we're going to take a look now at gravitational acceleration, it is different on every universal body, and that will depend on the mass and the size of the body, so the planet or whatever. So we're going to say that, and I'm going to show you how to derive this. Remember, we had mg, the mass of an object, was the force. Force was weight, and that was equal to g m1, m of the object, divided by the distance between the two objects. Now, if I'm talking about a planet, we could say the mass of the planet and the mass of the object. Notice that the mass of the object cancels out, and I'm left with the fact that the gravitational acceleration on any planet is equal to g times the mass of that planet divided by the radius of that planet squared. Again, the units are very important. The minute you're dealing with a constant, such as g, and we'll see quite a few constants from now onwards, when you deal with a constant, the constant has got specific units. So it's got meters cubed, kilogram per second squared. Those units are very specific, which means that I have to use the correct units for all of the other quantities that are inside that equation. If the Earth has a mass of what it is and a radius of that, determine the gravitational acceleration on Earth. So I'm going to substitute into that equation. G is equal to capital G, mass of the planet divided by radius of the planet squared, and I'm going to put 6,67 times 10 to the negative 11 multiplied by 6 times 10 to the 24 and divided by 6,4 times 10 to the 6, and I need to raise that to the power of 2, square it. And I land up with 9,77 meters per second squared. Double check that you can make your calculator do that. Try this example. So you're going to calculate the gravitational acceleration at a point that is that far from the center of the Earth, and the Earth is being given a mass. Press pause and then come back to it. Right, hopefully you've worked through this, and you're going to say G is equal to G m over r squared, so it's 6,67 times 10 to the negative 11 multiplied by the mass of the planet divided by the radius of where the position is squared. And this is further from the center of the Earth than the actual Earth's radius. If you remember in the last one, the Earth's radius was 6, something times 10 to the power of 6. So this is somewhere out in space, far away from the Earth, and I land up with 6,25 meters per second squared, which is less than the 9,8 times 10 to the, 9,8 meters per second squared.